Hello and welcome back. So today we've got a PowerPoint on free body diagrams. Nothing too terribly deep on this, I don't think. So just follow along. So a free body diagram, we've done these in physics, no matter which physics you took last year or freshman year, honors or regular. Basically, it's just you drawing of the object, or the object can be converted to a dot to simplify drawing it. I mean, if you're drawing a bird, you don't have to draw a bird. You can make the bird a dot. Okay, and then you label the forces that are acting on that object on your drawing. Okay. Um, so a force is a push or a pull that's acting on an object. A vector has both magnitude and a direction. The direction is given by the arrowhead and an angle very frequently. We'll give it by an angle. And the magnitude is either the length of the line segment, well, it typically is. And you can also label it with like 5 newtons or 30 newtons or something like that. So it's the how many newtons. So the moment or torque applied to an object has a direction as well. It's the twisting force about an axis of rotation or about a point when a force is applied at a distance from that point or axis. They have directions. We can have clockwise torque, which is not surprisingly the direction that the hands on a clock will move. Okay, or we can have counterclockwise, CCW, and that sort of thing. So that's how we'll handle the direction of a moment or torque. So a little bit of review on moment slash torque is moment is equal to the force times the lever arm distance. Okay, D is called the moment arm or lever arm is typically what I refer to it. It must be measured perpendicular to the line of action force. So basically, if this is your force, you draw a line through that force, okay, and then the torque or the lever arm, the moment arm, is the distance from the point or axis of rotation to that line of axis, perpendicular. Okay, and moment equals force times distance, or torque equals force times distance. Okay, and here they've got D labeled as the distance from that. Okay. Let's make a few free body diagrams here. Here we've got 3 books, Introduction to Engineering Design, Principles of Engineering, and Digital Electronics are choices here. So we're going to draw a free body diagram for the top book. Okay, so sketch the isolated object, so the top book. And we could, again, I usually draw the object as a dot instead of more of a drawing of it, but whatever. What are the forces that are acting on that top book, the DE book? Okay, well, gravity's pulling it down. Okay, and it's also in contact with the book below it. Okay, so when an object is in contact and is supported by a second object, the second object can be replaced with what's called a normal force. So basically, contact forces will typically be represented as a normal force. And normal doesn't mean like normal every day, blah, blah, blah. Normal means perpendicular, and it's perpendicular to the surface of the second object. Okay, so let's see, we've got the weight of the book. Okay, so weight of the book is down. Okay, and you can just represent the weight of the book as W. Okay, and you've got the normal force, which is up. Okay, which you can just, I don't know where they got these numbers from. And you can just abbreviate the normal force as an N force. Now these forces are in equilibrium. These forces cancel out. I don't know where, like I said, I don't know where they got these numbers from, but they look right. So our book must have had a weight of about 5 pounds. Okay? And the normal support book from the POE book was 5 pounds. And notice that the normal support force is perpendicular to the surfaces that we're dealing with. Okay, and when I add up these two forces, 5 up and 5 down, I get 0. And that's how we know we're in static equilibrium. Okay. All right. So if you're dealing with a more complex object, you probably, and you're trying to label all the forces acting on an object, you really don't want to convert it to a dot. You want to have more of a real representation of the object. When we do what are called trusses, which is what this looks like, you're going to want to have dimensions on it, and that'll help you out. And here we've got angles, and here we've got the forces acting on it. So, in my opinion, this isn't a true free body diagram, but it works for us. Okay. So let's create a free body diagram for the sled. So, what are the forces acting on the sled? Well, we've got a tension vector up here. So if you see a rope, you consider it a tension vector. Okay. We've got the weight of the sled, so we drew weight's always down. Okay. That's dragging against the snow, so this is the force of friction. Okay, so the force of friction is acting to the left because it's getting dragged to the right. Okay. There's the normal force because it's contacting the snow. The snow and the sled are flat, so the normal force is perpendicular to the snow, which is going to make it up. Okay, and the last one they put on was the force of tension from the ropes, F sub T. Okay, and they're drawing the angle on that. Okay, let's try again with a refrigerator. And so here we've got a guy pushing the refrigerator, so we're going to be the refrigerator itself. And let's label the forces acting on the refrigerator. All right. So let's see. Well, we're on planet Earth, so we're probably going to have a gravity vector going down, okay, or a weight vector. So that's the first one. So we'll draw the weight down. We've got this person pushing the refrigerator, so I might do that one next. Would be they call it an applied force. Okay. Oh, they do the normal force. Okay, so the normal force is contacting from the ramp. Now notice that it's not straight up and down here; it's perpendicular to the ramp, which is at an angle a little bit here. Okay, and so here we've got the applied force. You call this the person force or whatever you wanted to do. Really wouldn't matter. And as he's pushing the refrigerator up the ramp, there's probably some friction, and friction always acts opposite motion. So since the fridge is going up the ramp, the force of friction is going to go down and to the left of the ramp. Okay. I think that's all of them. Okay. Let's draw a free body diagram for a pulley system. So here we've got a mass 1 being supported by a rope from a pulley. And here we've got mass 2. So let's take a look at the mass 1 here and draw a free body diagram for it. We're on planet Earth, so we're probably going to have gravity going down, so weight vector. And what do we replace this rope with? What kind of force do we replace by a rope? A tension force. Okay. So force of tension F sub T. Okay, and that's it for rope for mass 1. Let's take a look by the movable pulley here. So this was a fixed pulley, and here we've got a movable pulley. So we're probably going to start with weight. Okay, so weight, they're called weight 2. Okay, because this is our second mass. All right. Now because we've got 2 strands of rope going up, we're actually going to have 2 force of tension going up. And so that's kind of what's different about this one, is it's got 2 ropes, 2 tension forces. Okay. And this is kind of an interesting fact too. The tension, this Ft right here, okay, is going to be equal to this Ft, which is going to be equal to this Ft, because it's all one rope. Okay. and the rope is able to freely move over the pulleys. So that's also kind of interesting. All right, on to some free body diagrams that are going to be really critical for our truss analysis, which is typically one of the most challenging thing we do all year, in my opinion. Centroids aren't that easy either, but trusses tend to be one of the really challenging things. But we'll get through it. Okay. All right. So different types of support reactions. So we're going to get into specifically when we attach something with a cable, rope, or chain. If we have a pin connection or if we have a roller connection. Okay, and the pin and the rollers are going to be probably the most important. We're not going to deal with this one. Okay. So let's see. So when we have a cable, rope, or chain, we replace that force. We've already said this. You replace that force with the tension force, Ft. Here they're calling it T instead of Ft. It doesn't really matter to me what you use. I know what you mean. Okay, so no big deal. Okay. When we talk about pin connection, so we're going to look specifically at bridges and trusses and that kind of thing here. We're not going to be getting to them today. That'll be another day, but we're just introducing some concepts. So when you build a bridge, everything isn't fixed. So in this case, we've got a pin connection that goes through here, and this is able to rotate if it needs to, but it cannot move up and down, and it cannot move left or right. This is another example of a pin connection here. It's just got a pin that goes through the bridge here. And again, this means it can't move up and down, and it can't move left and right. All right. When you see a pin connection, which on a truss will be represented as a triangle. I don't like this representation because it looks like it's just resting on it, but the triangle represents a pin connection. You're going to replace this pin connection with two reaction forces, one vertical and one horizontal. You're going to call one RAX and the other one RAY, okay, because we're dealing with point A. So this is RA in the X direction, this is RA in the Y direction. That's a reaction force at point A in the X direction. And then here we've got point B in the X direction, or point A in the Y direction. That almost came out right. All right. All right, so then we're going to talk about rolling connections. So the other connection for a bridge or that kind of thing is a roller connection. And this is an example of a roller connection. So here's the bridge resting on this roller. And now the roller allows the bridge to move left and right, so it doesn't exert a force at left or right. It allows the bridge to freely move either way. But it does exert a force up and down. Okay, the same way here. This allows it to move left or right, but it does not allow it to move up and down. So when we talk about a roller support, which is this picture makes sense, we're going to replace that by one reaction force. Okay, and in this case, this roller is exerting a force up. Okay, so RA in the Y direction. Okay. So bridges and trusses are often supported with one pin support and one roller support. This is called a simply supported object. Okay, create a free body diagram for a simply supported object. So if we look at pin connection A, all right, we're going to replace that with two reaction forces. Remember, okay, RAX and RAY. Okay, and then we've got a reaction force at B. Remember what we do at B? Okay, because it's a roller connection. All right, we're going to replace it with one reaction force, and that's simply going to be up. Okay. We're not going to worry about cantilever support forces. Okay. So I don't think I'm going to read this to you. Pause it and read it if you want to. Okay. So we just basically did this. I don't think we need to know this. Draw free body diagram of the entire British West. Okay, so that's where we're going to end on that. So good luck and have a wonderful day.